Okay. All right. So next question. How would you approach this?
Okay. There's so much to even look at. These are the kind of questions I'm not very good at because I get lost in them.
So here's the thing. Just follow the method I described. Okay. You have some text. First thing you do is you read it once. Okay. And then once you finish reading it, I want you to read it again, but I want you to highlight or underline the important pieces of information. Okay. And then we'll go from there.
Okay. So you need to find lead.
Okay. So specific heat of lead.
Yeah. You have 600 grams of it.
600 grams.
And you heat it to 100 degrees Celsius.
Mm-hmm.
So that's your starting point, right?
Yeah. So you heat 600 grams of lead to 100 degrees Celsius. Now you don't actually know. Well, let's read the whole question first, right? And then we'll sort of try to decipher what's going on. So what's the next piece of important information?
Aluminium container.
Okay, so you have aluminum.
Yeah. 200 grams.
Mm-hmm.
Has 500 grams of water.
Mm-hmm.
And initially at 17.3 degrees Celsius.
Mm-hmm.
And final temperature is 20 degrees Celsius.
Oh, the mixture, yeah. Okay, and then we're looking for is calculate the specific heat of lead. So we had already underlined that, but let's say we delete this here and we keep this. Okay, cool. So we've read it once, we've read it a second time, and we've underlined it. Now what we're going to do is we're still unclear on exactly what it is we're going to be doing. We know we have to find specific heat of lead. So now the next step is we need to just separate the things that we have that we're going to use and the things that we're looking for. So if I ask you right now, what are the given things? Given as in, what are the, like all these things we've highlighted, we're going to separate them into two categories. Things that are useful for us, right? Information that is given to us, and things that we're looking for, right? Information that we're trying to solve for. So if I wrote you don't have to do it this way exactly. I usually like to, I don't always write it explicitly. But let's say if I did, I would write I would make a little box, right, of my givens, and then I will make a little box for the things that I'm looking for. So what am I looking for? So given, all right, or rather calculate the specific heat of lead, right? So we're looking for Cl, let's say, right? This is what we're looking for. You agree? Okay. So what's given to us? So what I would do here, right, is I would say, okay, well, I have 600 grams of lead. So mass of lead is going to be equal to 0.6 kilograms. Now, it's always useful to put everything in kilograms.
Yeah.
Okay. Okay, so to measure the specific heat of lead, you heat 600 grams of lead to 100 degrees Celsius and place it in an aluminum calorimeter of mass 200 grams. It contains 5 blah, 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 at some temperature. So really what we're doing here, what the question's saying is we heated up the lead, okay? So that is its initial temperature. And then we put it in this other thing. So the initial temperature, Ti or T naught, I guess, of lead. How do you write it? Do you write Ti or T naught, or what do you use? Let's say if you wanted to write initial temperature.
Probably T naught.
T naught. Okay, so T naught L is going to be equal to 100 degrees Celsius. Right? Okay.
Yeah.
What else do we know? We place it in an aluminum calorimeter of mass 200 grams. So MC, or not MC, I'm sorry, MA, because it's aluminum that we actually care about, right? And A is equal to 0.2 kilograms, right? What else do we know? So first of all,
mass of water.
Exactly.
0.5.
Mass of water is equal to 0.5 kilograms. Right, great. So far, so good.
T0 of W is 17.3.
So here's the thing. It says they place it in an aluminum calorimeter of mass 200 grams that contains 500 grams of water, initially at 17.3 degrees Celsius. So this 17.3 degrees Celsius, is it the water, is it the aluminum, or is it both?
It's both. They're at equilibrium.
Exactly. So we would say T naught, okay, of W equals T naught of A, which equals 17.3 degrees Celsius. What's the last piece of information that we know?
The final temperature.
Okay, so we're going to say T final, so because everything's going to be at the same temperature at the end, right? So T final, I mean, I don't really know what subscript to use here, but let's say TF, just for whatever's sake. That's going to be equal to 20 degrees or 20.0 degrees Celsius.
Okay? It seems fitting for a question like this.
Sure. Okay, so now you see how I wrote down, so we had some clump of text, which was really confusing, and now we just isolated all the important pieces of information. And then it's really simple. I just have this table. Like I don't need to read the text again. Like I will only read the text again for two reasons. One, if I get stuck and I need more information because I might have missed something, or two, at the end of the question, when I recheck my logic to make sure I didn't solve some entirely different problem. That's what I need to make sure. And also, it's also important to make sure that you copy the values correctly. You have no idea how many times myself and other students have just copied blatantly wrong information. It happens. Okay.
Yeah.
So now this is all the information we have, and we're looking for CL. So and now that you have these, you have to sort of get from point A to point B, right? You want to get from whatever this information is. This is the puzzle, okay? This is what you have, and you have to get here. How would you do that? So let's say I make a little line here, okay? And below this line, we're going to solve the problem, let's say.
Well, you have the formula for specific heat capacity, again, Q equals MC delta T.
Okay. This is the formula for heat, or rather for, yeah, because you said equation of the heat capacity, which is, it's not true actually, right? It's the equation for heat. Or maybe I misheard you, I don't know. Perhaps that's the case. Anyways, so Q equals MC delta T, right? This is the equation that you have for this theory. Now, what do you do with this?
Yeah, so CL would be Q, right?
CL would be Q?
Yeah, so what you're trying to find, CL, that would be Q.
Well, let's think about that for a second. Don't we have a C here? How is this C different from this C? Because what you're telling me is that this CL is this.
You need to find the specific heat of lead. What's the difference between specific heat and specific heat capacity?
Nothing, I think. I think it's just another way of saying it. Yeah, that's it.
I'm confused. So when you're trying to find the specific heat capacity formula, Q is not the specific heat capacity?
Q is not the specific heat capacity. No, Q is the heat in terms of energy, right? Like the Q is just like amount of energy you need to put into it, and its units are joules. Specific heat capacity or specific heat is, I can see why that's a little bit confusing because it's like specific heat. But whenever you see specific heat, think specific heat capacity because they got lazy and they're like, we're not gonna say that part.
It's the values above, right? Where water is like 4,180.
Yes, absolutely. You can use those values.
So that's what we're trying to find. It is C in that case.
Yes, so absolutely. It is C.
Then we'll probably rearrange the equation instead.
Okay, but before we do that, because I agree we need to rearrange the equation, but before we do that, we have to set up the right equation, right? So you want to set up an equation that fits in all of these things that you need Okay, and then you're going to rearrange it. So now my question to you is, what is the equation that you're going to write that will give you, or that accurately describes the system? So let's think about this again. So we have lead that we've heated up, and then we put it in a calorimeter that contains water. So it's useful to draw a diagram. So let's say we're gonna get this specific. So let's say this is lead, right? This is PB. This is lead, or PB is the same as lead, right? And then we're gonna put this. We're gonna put this in some calorimeter that has water in it. That's what we're gonna do. So if I tell you once I put it in, what is the equation that describes this phenomenon? It would be what? It would be, this is the right equation, but this term here is going to have to change, right? Because you have MA, you have MW, you have TEF, you have you have T naught W, you have T naught L, you have. So how would you set up the equation?
So you have 3 masses and 3 temperatures. And here, that's only 1 mass, 1 temperature. So I'm assuming you'd have to have formulas that equate to each other.
Exactly.
You probably do 2 of them.
Okay. So how would you think about this?
So for example, the 0.6 kilograms of the lead, with the change in temperature being 100 degrees minus 17.3.
Okay, so which?
Oh no, sorry, minus 20, because that's the final temperature. So that's 80 degrees. And what we're trying to find is the C.
Okay.
Would be equal to the amount of energy you need for the mass of the water, which is 0.5 kilograms, to change 2.7, right? Because 20 minus 17.3.
Sure.
2.7.
But forget about the numbers for now. Okay, forget about the numbers. Like what I'm saying is the numbers come last. Okay, if you can write the correct equation, the numbers don't matter, because I could give you any numbers, right? So what I'm saying is, if we focus our attention on framing the correct equation, then you can use that for any type of problem, right? You don't have to like think of the specifics. I want you to think about the general equation. So if you have to write a general equation, you said the correct thing, by the way. It's just that like you're bogging yourself down with the details. So you said Q lead, right? This is MC delta T L, let's say. What I'm saying is that your QL is going to equal your QW plus your Q aluminum. Because exactly, because the system, what happens is that you have a super hot object, lead, that you're connecting it with 2 other objects, water and aluminum. And really, energy is never created, never destroyed. It is only transformed, which means that there's no other heat source in this question. So that must mean necessarily that the heat that is lost from the lead, because it's the hottest object, must be the heat that is gained from the other 2 objects.
This is the isolated system, yeah. So
exactly. You don't have any losses here, right? So let's say losses would be equal to 0. There's no, like, it's ideal. So really what we have is QL equals QW plus QA. And you see how QL is just, like we said, MLCL delta TL equals MWCW delta TW plus MACA delta T.
There's a lot.
Yeah, I mean, this is not the longest equation you'll see in your life, but it is. Just to give you an example, I've had ODE, ordinary differential equation problems, where the answer was 8 terms. So it was something like log something plus log something plus E something plus X something, and then this goes on for quite a bit. So you gotta get used.
And you call it OD? question?
ODEs, ordinary.
OD problem? That's
ordinary.
we might need to rename that.
Okay. So this is the equation of interest, right? So you see how we have all of the terms that matter. So let's say ML is going to be here, right? So let's say ML.
Yeah.
CL is what we're looking for, right? So CL is going to be here. And then everything else is just stuff in our, so delta TL, right, is just going to be 100 minus 20. So this is going to use this and this. MW is just here. CW is in our table, right?
Wait, can we use the table?
Yes, we can. We can.
And they don't have the mass for lead, right?
Yeah, they don't have the mass. They don't have the specific heat for
Sorry, the
lead.
specific heat for lead. Okay, that's interesting.
So all of these things in green are things that we have been, it has been given to us, or in some capacity. And really, now you can rearrange the question, and you can say, okay, well, CL is equal to whatever this is. I'm just going to copy it because I'm lazy. This divided by ML delta TL. And as you can see, so far I've written no numbers because I don't need them. Right?
This is crazy. This actually makes sense.
Yeah. So in physics and chemistry, okay, maybe not chemistry, but in physics, I mean some chemistry. In scientific problems, you use math. Okay. So if you know your math and you're comfortable with math, then you just have to put them in contexts, and then the math just works out the same way it always has. It's math. So now we can say, okay, well, what is our MW? Okay, it's 0.5 kilograms times what is CW? It's 4186. 4186. Delta TW is what? So it's 20 minus 17.3, so 2.7. This is an 8. Okay, 2.7. And by the way, do you see how this term here, delta TW and delta TA, are actually the same?
Yeah.
So what we can actually say is we can factor this out, right? We're going to factor it out because it's a common factor. And we can just say 0.5 times 4186, so MW times CW, plus MA times CA, which is 0.2 times, what is the C of aluminium? It's 900, so times 900. All of this times your delta T, which is 2.7, and then divided by ML, which is 0.6, times delta TL, which we said was, what did we say it was, 80?
Yes, 80 degrees.
Yeah, I believe, let me just make a quick check.
Well, the answer I got was 127.
127, by plugging in these things?
Yes.
And that is the correct answer. 127, what are the units?
That is Celsius per kilogram?
Not quite. Think about it. So it's specific
joules per kilogram.
Joules per. So look back at the equation. Okay, you know that Q is going to be joules, right?
Yes.
So and you know that M is kilograms.
Yes.
You know that delta T is degrees Celsius.
Yes.
So to get joules, you're going to have to multiply by joules, divide by divide by kilogram, and divide by degrees Celsius. Right?
Okay.
Does that make sense?
Joules per kilogram Celsius.
I mean, I just want to make sure that you're not just agreeing with me because I'm being too quick, but like you understand how we got that, right?
No, I understand.
Okay,
yeah.
just making sure. Okay, great. And so this is your answer. Okay, so far so good?
Yeah.
Okay. Any questions?
Surprisingly, I actually don't.
Okay, so you're understanding things. It's good.
Surprisingly, I do. That's the point.
It's great.